the glapping instability is that if the wind speed reaches the tracker's natural frequency.
Yeah, so it's a harmonics.
Yeah.
It's a resonant frequency.
Exactly.
Yeah,
yes.
gotcha.
Yeah, so the panel can do this.
Yeah.
Can get swaying.
Yeah.
And then once it sways, for example, like the wind comes from this end.
Yes.
If it sways up like a little bit like this,
Yep.
it can be pushed by the wind.
Yep.
And get damaged.
Yep.
So that's one thing we call deflation or glapping, or the movement is called glapping stability. The second one is the trembling. Same. That's depends on the natural frequency. And third one is that because the panel has become large and you stow at like 45 degrees rather than 30.
Yeah.
So it will have like a stronger wind.
Yeah.
So it can easily get damaged.
Yeah.
Yeah. Even it doesn't look like damaged. You might have like a lot of micro cracks within the solar cell.
Yeah. Yeah. Wow.
Thank you.
Okay, so that's interesting. That's the glapping, or what's the other term for it?
Glapping stability, deflation.
Deflation.
Yes.
All right. I wonder what that meant.
Yeah.
Glapping, deflation, and then you've got this, which is
like a trembling.
trembling,
Or,
and that's longitudinal along the whole length of the tracker.
Yeah.
And then you've got just the sheer force of a large surface area with the wind hitting it. Okay, gotcha. Wow.
That's right. So that's the challenge for the traditional tracker. And in order to cope with this, I mean, if you still want to use the traditional tracker and if you still want to cope with this challenge, the only way is to, invest more steel.
Yeah.
Yeah, you can make your torque tube maybe much thicker, add as much damper as you want. Yeah, that might help to reduce the deflation or other instability. But obviously, that just increased the cost to the tracker. And still, the panel are still gonna face like a very strong like a wind pressure.
Yeah.
Yeah.
All right. So you two things you solve with more steel, but you don't solve the wind pressure. Yeah.
That's right. Yeah. So very interestingly, the other day there was a tier 1 module company. They came and tell me. They said that the developer wants them to have a 3200 Pascal wing, like the wing pressure durability for the front. They said they just can't do that, but that's how they measured for like a certain degree tilt, angle at that side. That's like a wing region C. It's like a very high wind speed area. Yeah, but if we are going to use some innovation, we can actually solve that problem.
Right. Okay.
All right. I think before we doing this, we would like to maybe go out and have a check at the the difference between the traditional tracker architecture and the what we're going to introduce is the multi-point drive architecture.
Okay.
Yeah.
What are we going to look at it?
Okay.
Okay. Cool.
Let's go.
Let's go.
Okay. Okay. Right now we are in front of the very mature traditional tracker architecture here. So this is the motor that we have been discussed. So this is like the only fixed point for the entire tracker architect. And as you can see that there are like several dampers on each post. So these dampers will help to reduce the deflation. And these are the Longi 400 watt panels, so they are not that big, but if we're gonna increase the size of this panel, then you can imagine this tracker will be much longer. And also you can look at these purlins. Later on we will show you the difference between this one and the SkySmart 2, but let's just focus on these purlins first. So you can see that we have this very long bar to hold the panels, and on the other side we have these supports to give like more strength onto these purlins. Well, because this tracker will be the external tracker, so it will stow at a steeper angle towards the wing. For this one, that's 30 degrees. So all those panels were going to face a very strong wind pressure. So you will have to have something like this to give more strength for the panel to cope with the high wind. And obviously this will